All right. Thank you everyone for attending this workshop. Before I go into what I'm about to say, I just want to provide some brief context as to what this is about. So this workshop is mainly to provide you all with the conceptual understanding of pose estimation with vision for your autonomous. Mr. Harder planned this workshop before summer, and I'm just here to share with you all the knowledge that I've picked up during my years in FRC and FTC and help you guys make your own autos. So just a brief summary, some things I'll be going over. I'll be going over the different autonomous navigation types, the command system architecture, how to set up your own Limelight, vision-based pose estimation, and then I'll be running a quick demonstration for you all to look at. So there's two main types of autonomous navigation in robotics. The first type, which is the most simple, is dead reckoning. Now, this is where you apply power from a starting point, and you basically just use the wheel encoders and angle from the gyro heading to know where the robot is at any given point. This method does work pretty well, but it often falls prone to external forces like getting ran into by a robot or just driving over a game piece. And it's relying on output percentage and time ramp. Now, the second type, pose estimation, relies on two sources of sensor inputs. The first type is the odometry, and the second type is the vision or your camera system. Now, this is a lot more accurate because it has 2 points of feedback as opposed to only one. And this allows it to calculate its position and heading to localize itself at any given point. So to put things into perspective, what I have here is a video from last year at Houston Worlds of our team, FRC Team 687. This is one of our playoff matches. If you look here, I think we're on the red alliance.
3, 2, 1, crescendo.
Not right.
Off we go. Blue Alliance, a race into the center. Red Alliance. There's a whole bunch of collisions over there. We're going to look at the scoreboard. Red Alliance doing some work. Blue cleaning up as well.
So during this match, our robot on the Red Alliance starts off in the middle. And during this autonomous routine, we score a piece from middle, and the middle of the field is where a lot of the collisions in a FRC match happens. There's a lot of robots trying to make its way to mid to snag a note. And we got hit a couple times pretty bad there, but we were able to recover on our way back and score a couple of notes. I have a second video over here.
Here we are in match 13. It is do or die on Hopper, sponsored by Molex. 1 note left in the midline. That's going to get claimed by the Nerd Herd. 2370 coming back. 4481 going to take a shot. Looks like 6328 might be wedged.
So I'll be going over the software architecture design for basically how all of this is possible. But the main things you want to be looking at here are the subsystem, the command, and how this works is the subsystem, in this case, the drivetrain, uses the command to calculate different waypoints and calculate the errors of those waypoints. Now, this might look like a lot, but really, there's 2 main things you need to know here. I'll be going over this in a little while. So for now, I think you guys all have a Limelight 3As. I want you guys to set up your own Limelight and just get it running. But before that, I'll be going over the concept of pose and April tags. So the Limelight 3A allows vision processing in real time, and it does this through identifying different fiducial markers scattered around the field. And this helps the robot determine its pose or position at any given point using the angle offset and distance offset from the tag. All right, so if you guys all want to take out your Limelights, I'll be going over how to set it up. So just to clarify, when you're mounting the Limelight, if you want to calibrate the Limelight itself and work on changing the pipelines, you want to mount the Limelight from its port to a computer. And once you've got that, there's a link over here, limelight.local 5801. And if you enter that into any browser, it should take you to a Limelight dashboard here. And this is where all the tuning happening. This is where all the tuning happens. And when you're getting started with April tags, you want to make sure, first of all, that your pipeline type is on type April tags. And this will allow you to detect any April tag inside of its view. Can everyone see the Limelight dashboard? Can I rotate this? All right, so once we're at the Limelight dashboard, one of the first things that you'll notice is that your camera feed is pretty dark. And this is because the exposure is really low. So whenever you're trying to detect like an April tag, but it's just like too dark. So if I put an ID7 here. All right. Sorry about that, guys. I think I'll be continuing on with the Limelight setup and calibration. So when you're adjusting camera settings, there's a lot of like sliders and buttons that you can choose from, but really there's 5 main things that you want to be looking at. The first one being exposure. Exposure helps your camera see things when the environment is either too dark or too bright. You can adjust the light level there. Cropping is another method that you can use to like slim down or cut off parts of your camera feed that you really don't want to be using. And then for orientation, if you mount your Limelight upside down or sideways for whatever reason, you're able to flip the orientation around. And then as for black level offset and sensor gain, both of these levels they're pretty similar to exposure in that they affect the light level of the camera feed. But what's special about them is that it can change the sensitivity without affecting motion blur while the camera's moving. So if you guys want to play around with that, I have a couple April tags that you guys can use to detect. So if your camera's detecting the April tag, there should be a green border that shows up around the April tag fiducial. And that's how you know that the robot is able to see the April tag and it's able to take and receive information. And if it doesn't show up for whatever reason, there could be a couple factors. One could be pipeline tuning, but the other one could also be just like how flat the paper is. Because right now we don't have like a solid backboard, but on the field, the April tag would normally be against a wall and the tag would be flat. So this is just like an example of some tuning. And then here we have input. The input tab is where you do all the pipeline and lighting tuning. But in the second tab over, in standard, what we have here is the family of April tags, which you don't really want to mess with because we have the April tag classic 36H11, which is the one that's going to be used for both FRC and FTC. As for marker size, this is the dimension of the April tag. So FTC April tags are a little bit smaller than FRC ones. So you want to make sure that you have the right size. And then if you want to add ID filters, you can do so here. What this does is it tells the camera to only look out for certain April tags of those IDs. So if I put 1, 2, and 3 in the ID filter, the camera would only be looking for April tags with IDs 1, 2, and 3. Yeah. You can put commas, but if you want to do a range, you can type in a number, dash, and then followed by the last number. All right, so now moving on to vision-based pose estimation integration. Pose estimation data includes the X, Y, and Z position vectors, and also the yaw, pitch, and roll for orientation. Now, when we're using the Limelights, we're getting 3 pieces of information that we want to be using. We're getting the X and Y, and also the yaw of the robot relative to that April tag's position. And then with that data, it's then fused with the wheel encoder and IMU data from before for more accurate pose estimation. And it does this through weighting of the 2 inputs through the use of standard deviations, which I'll talk about more later. So here's the diagram from before of our pose estimation error loop. So over here on the top, what we have here is the operating system. This is the op mode that you program inside of the code. And in every autonomous op mode, there's an initialization sequence, phase, and there's also a periodic or execute phase. And this happens inside of the run. So with that in mind, we have two things. We have 2 things here, subsystem and commands. The subsystem, or the drive base, is what controls the individual wheel speeds, the wheel velocities of your drive. And then the command over here is what does all the correcting of the wheel velocities. Starting here, we have a robot kinematics. And that comes with the wheel encoder values. Using that information, we can find a pose 2D of the robot and keep back to it with the mouse player. Okay. So with that, with the odometry, that is 1 point of correction here. And these points go into a time debuffer, where it's then used as a current pose that is passed into the command. So inside of the command, we have a planned path, which is the autonomous waypoint that your team is using. And what happens there is if you have a path, that path is then split into many different waypoints. Many different waypoints, like often a couple milliseconds in length, spaced apart. And at any given point, these waypoints are compared to each other. And if there's any offset that is found, it's then passed into the chassis speeds. And through the use of a PID holonomic controller, it returns a corrected wheel speed that is then passed back into the subsystem for the drivetrain. And these requested wheel speeds go into the velocity control. And that's basically where the loop starts again. Now this keeps on running until the auto is completed. And while you're running it, if you want, you can hook it up to a telemetry server. If you have a data visualizer, you can see in real time the individual corrections of the wheels, of the wheel velocities. So what we have here on the left is our auto op mode. This is like the top level structure of the autonomous, and this is where we initialize the mechanism drive subsystem along with all of its wheels. And it's also where we initialize the limelights. So if we want to go into real quick the mechanism controller, the mechanism drive subsystem, sorry.
I'm not getting used to this.
Oh,
Okay. What do you want?
the mechanism subsystem.
Oh, okay.
So the mechanism drive subsystem comes with 4 wheels. And also we initialize a pose 2D later on. This pose 2D comes from the current estimated pose of the odometry. And then this is where we, this is our constructor over here. 4 motors, gyro for the angle heading, April tag processor, which is just the Limelight. Sorry, no, the Limelight 3A is the Limelight. April tag processor is the USB camera. So in FTC, there's multiple cameras that you can use. The Limelight 3A being one of them, but if you want, you can use a USB camera. Just for your own use. And then it comes with telemetry, which is just for data visualization. So one of the methods that we use to control the speed is returned from the mechanism controller, mechanism drive controller, which is the command. So inside of the command, you scroll up. So inside of the command, we have, inside of the constructor, we have a trajectory, the supplier, which is the pose of the robot that is constantly being updated. And then we have the 2 PID controllers for the X and Y coordinates. And then we have a profiled PID controller, which controls the angle heading. There's a couple other, we have a consumer here, which is the output wheel speeds. This consumer, what a consumer is it's a pointer to an object that can then be used inside of the mechanism drive subsystem. So I'll touch on that a bit more later, but if you scroll down, inside of our execute method, we have something called, the desired state. Now the desired state comes from a long list of different waypoints from your trajectory, and it finds a sample inside of the trajectory using an index for the current time. So once you pass in the current time, which you get from here, which is in nanoseconds, you get a desired state that you can then compare to get your target chassis speeds. Now the target chassis speeds is calculated using the pose desired state, and then it's applied to the 3 PIDs I talked about earlier. And then using that, you can set the front left, front right, and back right wheel speeds to its target wheel speeds.
You want to show the delta before move the code down or tiger. Yeah, oil and then over there.
Yeah.
Okay. Okay, most of them. Just confirm. Right. And down.
All right, so the subsystem here is the mechanism drive class that I talked about. And it has the robot kinematics here, which is the geometric makeup of your drivetrain. So like the distance that each of the four wheels are from the distance of the robot is what's stored in here. And then just set up the commands. And then for the command, which is the mechanism drive controller command, it takes in a panned plan path, and then it interpolates the next waypoint to find a chassis speed that is ideal for that given time. And then this chassis speed is then passed back into the subsystem through the requested wheel speeds, which is the Boolean consumer I talked about. And then it goes through a velocity control PID. And then that goes through to the robot in the form of wheel power. So I have an example demo that I can show you. It's a pretty simple auto. It starts on the right side. It translates diagonally to the front, to the top right. It does like a kind of like a box movement here, and then it comes back. So if you want to set up the data visualizer, I can run it on the field.
Okay. You want us talking about the graphic a little bit?
I can talk about the graphic. Okay, so what we see here is a snapshot of the data visualizer using Jupyter Labs. This orange line over here is the wheel speeds of the robot. So there's three main movements going out, and then there's three main movements coming back. So it's like a 1, 2, 3 motion going out, and then coming back, it's a 1, 2, 3 motion, returning back to where we started. So if you look at the graph here, this is the graph of the wheel speeds. But if you want to see the labeling, you have to, you can show it on the,
You want me talking about?
on here. Can you show that? So now I'm going to be running the demonstration of that auto on the field. So if you want to help me set up.
Is it this video or not?
That's not a video. That's an image.
Any questions? Say something. I know that's a little. Go ahead, just go. Open, further. Yeah. If I can move.
And so right now, is this is just encoders, or is this integrating anything else?
So this one just uses the wheel encoders and the IMU
Okay.
to localize itself. So this method works pretty well if you're running like a relatively short auto, but the longer the auto goes on, if there's like the presence of like any external disturbance, you'll notice that oftentimes the trajectory starts like drifting a little bit over time. that's the Auton. So. Yeah, so that was a brief rundown of the telemetry data visualizer using Jupyter Labs. So I've Mr. Kwan here to go over the data visualizer in more detail. So we have different variables here on the right. that that you can compare. So that being said, there's an auto path that I want all of you guys to create with that in mind. So the trajectory looks something like this. You go out at an angle, you drive to the middle of the field, and then you push back these 3 game pieces into the corner. So that's that motion, return to middle, second game piece, return to middle, and then the third game piece. So yeah, it's a pretty basic auto. We're just going to middle and then retrieving the 3 game pieces. You can do this on either side, so it should be able to be mirrored. Having said that, some things you want to keep in mind, some variables that you want to be tuning, are the wheel velocity PIDs. So, that's kind of like what the purpose of the data visualizer is. If you're running the auto, you want to make sure that the requested or the target wheel velocities match up with the actual wheel velocities. If there's a really big like difference between the two, then that kind of signals that you need to work on your wheel velocity PID tuning. If the wheel velocity is fine, but the path is still not going quite where it's supposed to, then you want to look into the path PID, which is the PID controller for the robot's pose. And then all of this is done so that you can ensure that the drive control is smooth, accurate, and able to go where it needs to be. So yeah, I think with that being said, I think that pretty much concludes the workshop presentation. You guys have any questions, feel free to ask. And yeah, good luck with your autos.